Okay, so here's how I'm going to prove it. The first thing we have to accept is that between 0 and 1, from 0 to 1,
yeah,
there are uncountably many numbers.
Okay. Yeah, that sort of makes sense.
Okay? So do you believe that?
Yes.
Yeah.
Do you believe it?
Mm-hmm.
Okay.
Because you can make more numbers. One.
Yeah. So as long as you accept that, which you're going to have to accept, then I can show you. So what I'm going to do is I'm going to write all those numbers in binary. So I might write a number between 0 and 1. It's always going to start 0 point something, right?
Yeah.
1, 0, 1, 0, 0, 0, 1. Like that. Or what's another one?
Like 0.1 1 0 0 0 1. Just 1 1 0.
So I just write them in binary.
Yep.
And I produce. Do you think every number can be written? Every number between 0 and 1 can be written in binary?
Yeah.
What do you think?
Yes.
Because every real number can be written. Or every number could be written in binary.
Yeah, it seems like it. Because all you do is you just, whatever your number is, you subtract away, you know, a half.
Thing
Or
that works.
if you can't subtract away a half, then you put a 0 there, then you try to subtract away a fourth, etc.
Yeah.
Okay, so there we go. And these are our numbers. Now, what I'm going to do is I'm going to take pi and e, and then I'm going to write down the swap. So 3.14159, 71828. And then, so here's the first digit, second, third, fourth, fifth, sixth.
Mm-hmm.
Okay, and all I'm going to do is take my digit places, and I'm going to write a 1 if I swap them, and a 0 if I don't swap them. So maybe for my swapped number, I'll swap the first digit, not this one, not the third, but the fourth, the fifth, the sixth, not the seventh, etc.
Okay.
Mm-hmm.
And what do I get when I write down my swaps as
Well,
ones
you
and
get a
zeros?
binary number.
You get a binary number.
Yeah.
And how many different binary numbers like this are there?
Infinitely many.
Which infinity?
Uncountably infinite.
And each one of these represents a new number that we created. So that was Joel David Hampkins' argument as to why it is unlikely that you produce a rational number. Because you have uncountably many numbers you can produce, which is a larger infinity than countable infinity. And where does countable infinity come into play here?
Well, I mean, you could count the number of digits that they have.
Well, it relates to rational numbers.
Well, there's countably infinite rational numbers.
Right, there's only countably infinitely many rational numbers.
There's uncountably infinite combinations.
Yeah, so you have
that can make.
uncountably many numbers, which means it's a larger infinity. It means, so you're not likely to pick a rational number, or to create a rational number. It's just like if I pick a number between 0 and 1 at random, it's not likely to be rational.
Yeah.
So give me a number between 0 and 1.
0.111111.
Oh my gosh, you picked amazing. You picked a rational number. What are the odds? So why is it unlikely? If you really truly pick a number at random between 0 and 1, why is it likely to not be rational?
Well, because there are so many numbers between 0 and 1.
If you're picking all the digits, it's just going to be a random string of digits,
right,
which is not rational.
Yeah.
And you can even choose it randomly. Choose a 1 or 0 here, 1 or 0 here.
Right, and so it's unlikely to sort of have a repeating pattern.
Yeah.
So that's why. But when you picked one at random, you just picked 1/9, right?
Well, yeah.
Because we don't have rational numbers between 0 and 1.
It's hard to pick a number with no pattern.
Yeah, so that's kind of the amazing thing, is that like almost any number you decide to pick at random, almost any one of those numbers is going to be rational.
Yeah.
But in fact, it's actually almost impossible to pick a rational number randomly.
Yeah.
So that's cool. All right, good work, guys. This is a fun problem. Good job today.